Hi, I'm Emma Molyneux from Blue Pearl Software, and I'm joined by our CTO, Scott Bloom.
Hi.
If you're not already familiar with Blue Pearl, we're a leading provider of design automation software for ASIC, FPGA, and IP RTL verification. Our users are RTL developers and verification teams in military and aerospace, semiconductor, medical, and communications industries who want to avoid costly and time-consuming design spins due to simulation versus hardware mismatches, invalid constraints, and clocking issues. Over the next few minutes, Scott and I will discuss how our visual verification suite complements Microsemi's Libero design software, improving the reliability of space-bound FPGAs as well as shortening the overall design cycle. I'm sure you're all aware that in space there are no second chances. If a design error slips through, it can be catastrophic. To help safeguard, there are industry standards focused on aspects of a design, from hardware and software to mechanical. It's all about reliability. Microsemi is the leader in high reliability FPGAs for space applications, and our solution is designed to ensure your RTL, VHDL, Verilog, System Verilog, is also highly reliable to program your devices with. DIR 254 is an example of such a standard. The standard utilizes a requirements-based design and verification approach. This means the entire hardware project revolves around a formal set of high-level requirements. Prior to writing RTL, each of these requirements must be captured, given a unique reference name, and reviewed for a variety of criteria including understandability, testability, and verifiability. The standard defines the hardware design processes and breaks it into these phases: planning, requirements capture, conceptual design, detailed design, implementation, and transfer to production. Verification is required at each and every phase of the design process and can take a significant amount of time throughout development. During this RTL development, simulation is not sufficient enough to find all possible issues in a design, and clocking issues can even be missed in the lab. Our visual verification suite complements RTL simulation solutions provided by EDA and FPGA vendors, like those provided in the Microsemi Libero design tools. We ensure code quality with advanced linting and debug, address clocking issues with clock domain crossing analysis, and SDC quality with automatic constraint generation. Our built-in Microsemi library support streamlines the verification process, so users can verify as they code instead of waiting for simulation, synthesis, and place and route, as well as find issues before they make it into the lab, where they can be very difficult to debug. The integrated environment is designed to swiftly find and fix finite state machine issues, structural issues, set reset issues, clock tree issues, safety issues, coding conformance issues, and metastability issues. Additionally, on the way to tape-out, our management dashboard provides easy tracking on the quality of the design based on required checks. It is also ideal for reporting during design reviews and audits. Okay, I've talked enough. Scott, can you explain what types of issues our visual verification suite can find and give our viewers a quick demonstration?
Sure. Blue Pearl's visual verification suite directly supports Microsemi's libraries, including the new RTG4 FPGA family. Let me bring up the tool and show you how. Selecting RTG4 or any of Microsemi's libraries, when the user instantiates an RTG4 gate in the RTL, Blue Pearl can understand its functionality. This allows the tool to trace clocks and data paths through the design, allowing it to understand clock domain crossings.
Great. Can you tell me about some of the technical problems that RTL Analyze can find in a typical design?
Sure. Some of the issues we find are structural, and some are clock domain crossing problems. It is important that these are resolved as early in the design flow as possible. By finding them early in the design flow, you minimize the cost of resolution, as well as minimizing the potential of the mistake making its way into production.
What do you mean by structural problem?
Let me show you in the tool. In the analysis results window, it identified a mismatch in bit range during an assignment. In this case, the size of the signal being assigned to is smaller than the source signal. You can see the message in the display and the RTL code that caused this. The target signal, being smaller, will cause a signal truncation, typically when this occurs. It is not what the designer intended.
That's interesting. Can you show us another coding problem, and is this the kind of problem a customer can check for in an internal coding review?
Another one that you can see in the same analysis results window is a missing case default. Many companies, for coding safety reasons, require a default condition in all case statements, even if all the cases are defined or there is no way for a missing case statement to occur. As to the question about code and review, of course, in reality, many coding issues can be found with strict line-by-line peer coding review sessions. However, the problem with that is time, money, and the quality of results. First, it's extremely time-consuming to have every line of code in your design validated for the hundreds of types of checks that we do. That time will not be free and could be better spent having the engineering resources work on enhancing the design itself. Second, engineers, even the best of us, make mistakes. No one intentionally creates bad code. For every mistake found by another set of eyes, it might take a third set to decide which answer is correct, the original code or the newly proposed fix for the issue. Finally, what happens when there is a code change, even a code proposal that comes out of a code review? You would have to go through every check by hand that your team performs on the complete design change. So yes, while it is possible to run these types of checks by hand, automation will provide consistent results much faster.
So what is a structural check? Can you show me an example?
Sure. No one today creates their designs 100% from scratch. Everyone uses third-party IP. Connecting that IP correctly can be a challenge. One common problem that happens is not connecting all your nets or a pin while instantiating the IP. RTL analysis generates an undriven but loaded message when a net that drives part of your design is left undriven, as opposed to a net that was unconnected internally and can typically be ignored. Blue Pearl's live log file allows the designer to search for messages and then hover over design objects in the log to get full design information about the object interactively.
How do I find out more about this message so I can figure out how to fix it?
Blue Pearl can show you in the schematic where the undriven net is and trace the paths to their destinations. If there is an undriven net that drives logic, it will be floating. This could cause failures in the design.
If finite state machines are used in the design, can our visual verification suite help me?
Yes, it has an FSM viewer that will show the states and transitions of all the state machines in the design. In this case, it identified a terminal state and an unreachable state. This can cause failures in the design.
I understand that Blue Pearl can find clock domain crossing problems. Are these problems not found during simulation?
Emma, it's possible. However, simulators only run what you tell them to in the test bench. There are two aspects to fixing a CDC problem. First, you must locate the CDC. The simulator does not help you with this. You have to know every CDC crossing your design beforehand. You would also have to know the clock system of every IP block in your design. Are you sure every clock in the IP is synchronous? The second aspect is verifying that a CDC is properly synchronized. A simulator can help you here if you are able to recognize what an improperly synchronized waveform looks like, and you are able to create a stimulus in your test bench that produces an unstable event at the crossing. The result is many CDC issues find their way into the final product and are very difficult to find in the lab, and are even harder to resolve in the field. Let me show you how Blue Pearl reports synchronized and unsynchronized CDC paths in the RTL. Blue Pearl's visual verification suite can show synchronized and unsynchronized clock domain crossings. Here is a double register synchronizer. The schematic diagram shows the source and destination clock as well as the CDC data path. I will now show you an unsynchronized path, which can cause metastability issues that will need to be fixed. Also shown are the source and destination clocks as well as the clock crossing location.
It looks like our visual verification suite can produce valuable messages that can identify problems in the designs we code versus waiting for results from downstream tools or in the lab. How do we keep track of this information?
The suite provides the management dashboard for this function. The management dashboard displays a histogram of the messages for each run. This allows the user to track the results of analysis. The types of messages are also tracked, as well as if the messages were reviewed and waived. The number of outstanding issues should approach 0 as the project is nearing completion. The management dashboard also includes a design sign-off feature to ensure all company-specific rules or standards, such as DO-254, have been complied with.
Thanks, Scott.
No problem.
In the traditional simulation, synthesis, place and route flow, many issues only show up during the lab debug phase, where design changes are the most costly. Our Visual Verification Suite provides a step before simulation to find problems early in the process, reducing long iteration cycles to accelerate development, improving quality, and reducing risk. For more information, please visit the Blue Pearl Software website or reach out to a Blue Pearl representative. And finally, thank you from both Scott and I.
Thank you.